Ladies and gentlemen, welcome to session 2 of, even get a nice video image of Miriam. Hello. Okay. Yes, welcome to session number 2 of our biomechanics session. And title is exactly the same as last week: as strong as necessary and as weak as possible. The golden rules of mechanics in osteosynthesis session 2. So just that we're all pretty much on the same page. I would just sort of, maybe this is the first time you listen to this mechanics or biomechanics talk. That's why I would just like to sort of run you through what we've been talking about last week, just very briefly, maybe 5 minutes at the most, so that we're all pretty much on the same page, if this is okay with you. And then we can continue with the new stuff, which is this time a little bit more practical. So I will talk a little bit more about implants, more precisely about, obviously, about Medartis implants, but nevertheless, to me, it's always the important thing that you learn how the principles work. Now, what's again the aim of the session? Obviously, I would always like to point out those aspects that you usually cannot find in a brochure. A brochure is usually a sales tool, and in a sales tool, you have those typical marketing things. And whereas here, I would like to point out more the engineering side, the engineering aspect. That's why I would like to talk medical engineering rather than sort of give you the typical sales talk stuff. I want you to create a certain understanding for our challenges that we have from the engineering standpoint, and certainly let you participate in a way in the decision-making process of a good implant design. You see, the stuff that we usually design and produce, these are decisions that we take at one point in the past. And the whole development process can actually take months, if not even years, sometimes, before we actually hold something in our hand that properly works. Okay. Then obviously learn to differentiate the good, the bad, and the ugly. As we all know, a plate is not a plate, and not a plate. They're all different. Some of them are just sort of copycat things. Others are really sort of very innovative, and you can actually point out certain aspects where these innovative products actually have their advantage compared to the sort of mainstream stuff that's out there. And last but not least, this is the main topic today, is actually that stability is not everything. Sometimes less is way more. And in order to create obviously a certain understanding, I have a few practical examples of our product in comparison maybe with some of the products that are out there in the field, and so that you know where we stand. Okay, now review of session 1. That's what we're currently doing. Then a little bit an excursion towards stability and stiffness, influence of geometry this time. So maybe you remember, actually last week we talked about mainly about metal, to be precise, about titanium, and why we've actually chosen titanium as an implant material. And geometry was not actually highlighted then. Now is the time to do so. So stability, less is sometimes more. So why some of our implants are way more delicate than the stuff that you usually find out in the field. And there's a huge difference when we talk about flexibility and rigidity. Those things should not be confused. Lots of people think actually if something is flexible, it's not stable to do the job, and it really needs to be completely immobile and completely rigid if you want to have sort of a proper fixation. And I'm afraid this is sometimes not really true, because life is all about flexibility, elasticity. The way we are actually built, we are usually sort of set up by obviously elastic structures. Our bones are not rock solid, so when you load them, they tend also to flex a little bit under load. And this is what I would just like to highlight, that actually flexibility is a very important factor in that respect. Once again, if you have questions after the presentation, please feel free to ask me, Mr. Walter. That's what it says here. Please ask me after the session, if this is okay with you, unless you have a super urgent question. So you can actually sort of also type it into the chat field, and I'll at least try to then, towards the end of the show, to sort of pick those questions up. Again, if you like to do the hand raising thing, so click on participants in your status bar. then the participants list will appear, and now you have the option, obviously, to either click the button or raise hand, or you can also you can also, so there's a raise hand button, or maybe there's a little hand that you can actually click onto that turns then blue. And this will then tell Alex. Alex is actually 80 kilometers from where I am at the moment. I'm directly in Basel. Alex actually sits in his home office, and then Alex will unmute your microphone. And when it's your turn, you're actually free to ask the question so everyone can actually hear what you want to learn. Okay. Now, quick sort of review of what we've learned so far. So basically of session 1. And remember that one, stress is inside of bone. Now, obviously any kind of mechanical object, and this includes obviously bones as well as cars and scaffoldings and you name it. Actually, every time you overload a structure, overload leads to destruction. And in our case, it leads to bone fractures. So therefore, function of the bone is not given any longer as we have an unplanned joint. Maybe you remember that one from last week. Now bone, and to me, always a super important point, bone is a viscoelastic material. So it actually sort of acts very differently if you load it very quickly, so at a very high speed, or at a very low speed. So if you gradually sort of load bone, the fracture pattern will look different compared to the same load, but applied in an extremely short period of time, okay? So not just the magnitude, also the speed plays a vital role. So in bone, sudden application of load means that the energy simply cannot be absorbed fast enough. And so therefore you then have these high velocity kind of injuries where you have those comminuted fractures that just explode completely, even if your bone is more or less healthy. So you don't need to be completely osteoporotic to end up with a highly unstable fracture, a comminuted fracture. So just to let you know, those are the kind of factors that play a role when we talk about bone. You also learned about, obviously, the different stress modes. So what is actually bone or any mechanical structure subjected to? So we have the tensile load, we have compression, shear, torsion, bending, and also mentioned, yes, last week that bending is obviously sort of an overlap thing. So you have in the outside portion of whatever you bend, you have the tensile load, so the tension on this side relative to the neutral line that you see there, whereas towards the inside of the bending object, this is where you have then all the compressional loads. So this actually changed. So when you alter now from left to right, so the compression side becomes the tension side becomes then the compression side, and vice versa. So this is what happens when you bend an object. This obviously, especially when you overdo it, when you overstress the bone, we end up with various fracture types. And today, because you want to go away from sort of the standard easy peasy stuff towards more the comminuted side of things. And that's why the highly complex fracture family is obviously in a big interest of ours, because when we sort of started actually with Medartis, and especially with abscess, especially hand radius, we always wanted to serve the surgeons with pretty much anything that you need for a proper plate screw bone repair. So no fracture complex enough for us, and this was the plan. So going away from just the average mean kind of injury, we wanted to be able to obviously deal with the high complex stuff, and which is one of the reasons, and I did not mention this yet, why we introduced actually locking constructs to hand surgery as the first company ever on this planet. So just to let you know, this is just the way it was some 18 or 17 years ago, so that you also have heard this and that I've mentioned it. All right, now, since we talk about comminuted stuff, obviously the internal fixator is in the limelight at the moment. So therefore, we have obviously a bridging or bypassing effect, as we call it. So whenever you actually load the very unstable bone and you have fixed it with an internal fixator, so a locking construct that locks distally as well as proximally of the fracture, any kind of load that you apply now to the joint bearing part will be transferred into a distal bending moment. This bending moment travels along the metalwork, and this bending moment is actually fed back as a proximal bending moment into the radius shaft in this particular case. But once again, this could also be a tibia. This could be any kind of bone, doesn't really matter with a defect. So the principle is plus and minus, always comparable there. And so we end up obviously with a zone of reduced stresses. So from the distal towards the proximal locking screws, this is virtually, I don't want to say it's completely load free, but it's definitely reduced stresses there, which means that the bone here can actually heal. So this gap eventually will gradually close over time as long as you have bony contact here. There's not even the need to fill this void with any kind of bone graft or so. So that's simply not necessary. In the majority of cases, I have to say, I don't want to say there is always a situation where you have to stuff something inside, even with our material. So there's usually no end to complexity. All right. Now, load bearing means this implant has to take load all the time because you have your flexor and your extensor tendons obviously sort of pulling on both sides, on the dorsal aspect and then the volar aspect, which means you have a constant load actually on your joint, which means that there is always bending, or if the force is actually sort of applied offset a little bit, you can also have then torsional loads as well as shear loads, etc. Now, maybe you remember this from last week. This was sort of a little bit of a hypothesis. I just wanted to provoke you a little bit there. So hypothesis stability is the key to success in bone repair. We assume that this is true. Hypothesis 2, products usually fail because they're not strong enough. Okay, so we would conclude actually that the stronger the construct, the better the product. And in the majority, I would say in the majority of comparative kind of metalwork studies that you find in the various journals, this is actually the outcome usually. There's always this little paragraph towards the end. We are not quite sure how the extra stability will influence the healing process. But the message is always, if you want to be on the safe side, just choose the strongest one, choose the most stable one, then you're definitely on the safe side. And I say, is the stronger construct really the better product? To be honest with you, I don't think so. I don't think this is not always the case. Stability, high stability is obviously paramount, but we must not confuse ultimate stability with adequate stability. Those are different things. You need to know to which level you want to work to, and then we can actually talk about, is the implant strong enough, or is it over-engineered? Is it overly strong? And then certainly it's maybe has a negative effect on the overall structure that we try to rebuild. Okay. Now, since the screw plate construct partly has to take over the function of bone, which means now we have moments, bending moments on the joint bearing aspect. So in the YZ plane, in the XZ plane, we have axial loads. And all this leads now certainly to a reaction in our poor plate. You see, the plate has to take now all the bending, the shear, the compression, the tension, and the torsional loads that the bone usually carries for us. But since the bone is not in working condition anymore, the metalwork actually has to take over that stabilizing aspect of the bone. So this is sort of just an image of I would say this is the most basic distal radius plate that we have in our portfolio. It's the so-called extra-articular plate that is designed for fractures where the bone, the joint bearing part is not involved at all. So it's sort of just a metaphyseal fracture that is dorsally maybe comminuted. So just has the tendency to tilt over towards dorsal, but the joint pairing parts, radiocarpal joint, distal radioulnar joint, is perfectly intact. And if I would just take now a big saw and I would just sort of cut the whole construct into pieces, so basically I would just sort of cut this off and would remove the distal part, you could actually see now in the cross-sectional area of the bone. So you have your cortical shell, and you have obviously then in the center in light gray, you actually see hang on, lost my mouse. Oh yeah, there we go. The light gray is basically your cancellous bone that you see. Now, if you do a little comparison, And obviously, you see, when you put now a plate on top to stabilize this sort of represents just sort of the cross-sectional area of metalwork that we put on top of this particular bone. You usually have a cross-section in this region. This is just rough estimation, so just calculated this to be sort of a tube with 20 millimeters in diameter. So this gives you roughly 300 square millimeters of bone tissue to take all those loads, obviously tension, torsion, etc., etc. And this is now taken over by a piece of metal with only a very small cross-sectional area. And again, just an estimation, roughly 20 square millimeters. And this depends now very much on the manufacturer. So are you actually buying from competitor A, B, C, or D? They have different concepts, they have different heights, widths. So why is this so? Why do we see so many different kind of designs? And every company will actually tell you, or at least should have a justification why they're actually doing this. And this presentation should actually shed a little bit of light on this decision-making process, why companies are actually choosing certain kind of dimensions, certain kind of cross-sectional areas to stabilize the bone. And sometimes, you see, this can be a good thing for the mobile tissue, so for all the flexor and extensor tendons that have to run across the metalwork sometimes, or it can also mean that the designer designed just a plate that was good for actually repairing maybe a plastic bone or something, but there was no real attention actually given that there is also gliding tissue that has to cross obviously the metalwork. Now, especially in hand surgery and foot surgery, these are vital things. Every 1/10 of a millimeter decides upon a good or a bad return to mobility. You see, even if you have a nicely closed and you have a beautiful X-ray of a finger that has actually grown together perfectly well with a super plate that you've inserted, but the plate is so unbelievably bulky that you're not able actually to perform actually your normal biological or anatomical movements. So therefore, the job is not done correctly, and I just like to give you a little bit of an explanation there. So, is a plate, is a plate, is a plate? No, certainly not. They come in all shapes and sizes. They come big, small, big cross-sectional area. Sometimes they have actually 2 arms that actually cross the fracture. And all those things obviously have a certain meaning for us. And we have to understand that obviously due to the design, they also behave a little bit different when it comes to testing, for instance. Okay. Now, just quickly, again, coming back to last week's session. So why is Medartis actually a genuine titanium company, right? We don't use any other material, just titanium in its various sort of grades. And simple as it is, because it has the perfect features for long-term implantation. You can also ask other manufacturers. There are manufacturers that will purely work with steel. Wonder what they have as a justification, don't know. But having said that, we're not alone on the planet. There are also other companies who will only work with titanium when it comes to implants. So therefore, but one of the reasons is actually it's a magnificent biocompatibility aspect. You can just leave it inside. Titanium will never actually cause. I should not say never actually, because this is a qualitative statement. In the majority of cases, it does not create any kind of tissue reaction. So any kind of body reactions, unless, and I have to say this, unless the company has actually chosen maybe a wrong surface treatment. Maybe the surface is too rough and you have a bony ingrowth or something. Those things can certainly happen due to the friendliness of the metal. And the other beauty is obviously the fact that titanium is perfectly non-magnetic. So therefore your patient is MRIable, which with a steel implant is actually not that easy. We have an extremely good weight to strength ratio. So titanium has a very low density of 4.5 kilograms per liter per cubic decimeter, or 4.5 grams per cubic centimeter. So about the same thing. Compared to steel actually comes with 7.8. So it's about 2/3 more in terms of weight, which is obviously in a finger implant or a radius implant. Really not that tragic, but it's always something that you try to go for, not to implant lots of mass, lots of volume, but actually to have something that is strong and therefore also feasible. Beauty about metal in general is the ductility, the malleability, because sometimes you need to contour your plate to make it actually fit the anatomy. Flexibility and elasticity, I mentioned this before. You cannot just accept an implant that is absolutely rock solid and completely immobile. We have to understand that bone flexes under load. Hence, our implant also has to flex under load. And if it's not flexing, then wherever you have actually the interface between bone cells and between metal, this is then where you have some kind of reaction. So where the living is actually meeting the dead material, the metalwork, right? So we have to be careful there. Then obviously titanium, also the beauty for the ones who already appreciate this, titanium is color codable. So therefore, when you sort of apply an anodization process, you can actually change the color appearance. So therefore, you can give it any color of the rainbow, blue, red, green, yellow, purple, doesn't really matter. And you can then utilize, obviously, the color information for communication. A green screw is, for instance, in Medartis terms, a self-drilling screw. A blue plate, a blue screw is actually a locking construct, a golden plate, a golden screw, non-locking, and all those things you could not do with vitellium, cobalt, chrome, or steel, because these materials are always silver, doesn't matter what you do with them, okay? So therefore, it's not that easy. All right. Now, I just sort of flipped this over, this image. So basically what you see at the moment is actually, this is my arm. So this is volar here, this is dorsal there. And this is exactly what we see here on the image. So volar here, dorsal there. Now, since the screw construct partly has to take over now the function of bone, hence bending, shear, compression, tension, and torsion, we need to understand that wherever the gap is, this is where everything happens, okay? This is where the joint bearing part is actually meeting the shaft part. So all the forces are bundled in this particular point, okay? So when you take a look at this X-ray, and this is a dorsally displaced distal radius fracture, so that is now tilted about, I don't know, maybe 30 degrees or so from its normal 11-degree kind of angle where it should be. We have now two main parameters that influence the plate design. One is material. Remember, we talked about material aspects last week. And two is actually now geometry. Now, geometry was something I was not actually sort of pointing out so far. So today, it's mainly about the geometrical aspects. And there is a little formula that goes with it. So that means the maximum bending moment means that you have to use a material with that has a maximally allowed stress. So therefore, it's a difference if you use titanium grade 1 with a low tensile strength, or if you use titanium grade 4. Okay, there is Alexander just raised a quick question from Paulina. Can you explain, if every titanium implant is non-magnetic, what happens with other materials? Well, titanium is a non-ferritic material, so hence it is non-magnetic, or it's not really magnetizable. What happens with other materials? Now, obviously, all those ferritic materials like stainless steels, they certainly sort of will create some kind of artifact. So if you take an MRI, you get sort of a very bright image. It looks like a spark. So you can't really use those MRI images actually for sort of giving out a statement. Did you have a good bone healing, yes or no, or is it in a good position? Because it's like looking in a flashlight of a camera, right? You're just blinded basically. And in titanium, as it is non-magnetic, only when you have extremely high Tesla, so when you have extremely powerful MRI machines, there you might see a certain artifact, but in the majority of machines, nothing is really visible, or very, very, very little artifact, so you can really use it for proper identification. Okay, I hope this answers. Oh, there's another question from Brandon. Is titanium less likely to be irritable to a patient than other metals such as stainless steel, and why? That's a good question. Why? Well, part of it is titanium is an inert material. So once it creates a titanium oxide layer, for whatever reason, the body cells don't seem to recognize it as a foreign material. So in actual fact, it's so tissue friendly that potentially bone cells like to grow directly or cling directly onto the titanium surface unless it is very smooth and polished, right? But if you take, for instance, a dental implant has a very rough surface, because the idea there is that you have what's called the so-called osseointegration. You want those bone cells to directly grow onto the surface and to anchor basically around the implant. Now in osteosynthesis, this is not what we want, because certainly we want the gliding tissue still be able to travel free and easily over the titanium surface. Now, if you go back 20, 30 years, manufacturers were not quite aware of this. And sometimes you ended up with a rough surface, maybe something that was sandblasted or glass bead blasted. And there you had the problems actually with what's called adhesion or bony ingrowth onto the implant, which means you had to chisel the implant out when you wanted to remove it. Now, these days, I think we have quite a good understanding. And again, all titanium manufacturers have their own little recipe when it comes to sort of finishing the plate surface to reduce the risk of bony ingrowth. And to be honest with you, this is an important thing, because the last thing you would like to have is obviously to have a good bone healing, but gliding tissue not able to travel across the metal surface. So therefore it's more of a surface treatment aspect that we need to concentrate on. Happy with that? Good. I hope so, at least, anyway, because we have to continue. Right. So maximally allowed stress times the so-called, and now we come to a point, the so-called section modulus. Now, the maximally allowed stress is purely a material parameter. So depending if you use stainless steel, if you use titanium grade 1, 2, 3, 4, whatever, whereas the section modulus is purely a geometrical parameter. So is the implant broad and not very high, or is it very high and relatively narrow? So these are the kind of aspects that help us sort of calculating, obviously, what's called the section modulus. And I would just like to run you through this, because for an engineer, this is an important point, right? Because you see, sometimes you cannot make material stronger than it already is. Titanium grade 4 has a certain maximum strength, and I cannot increase the strength any further. So what I need to do then to make the whole construct stronger, I need to play now with the geometry of the cross-sectional area that goes over the fracture gap, okay? So maybe as a little reminder of last week, titanium grade 1 has a very low tensile strength of 240 Newton per square millimeters, so not overly strong. Grade 4, already 2.5 times as much, 550 Newton per square millimeters, and titanium, aluminum, vanadium is already offering us 860. So therefore, if we choose from those materials, we always find something that has a suitable stability, so that allow us actually to reduce the size of the implant to an acceptable size, okay? And that's obviously something that's important for the clinical outcome at the end of the day. Okay, now why are some plates big and bulky? So obviously plates come in all shapes and sizes depending on the manufacturer. And if you should wonder, are those other companies, are they not clever enough to come up with a nice thin plate? Nope. Sometimes they have to use soft plate material, because it depends all now very much on what kind of locking mechanism they actually provide for an internal fixator principle. Some companies actually have a soft plate metal for the plate, and an extremely tough material with a high tensile strength for the screw, so that the screw can actually sort of cut a path or tap a thread inside of the plate upon insertion of the screw. Those companies, obviously, they can only sort of compensate the weakness of the soft material by adding extra metal to their cross-section. So they cannot actually go for something that is very thin and very small. They have to beef it up to make it rather bulky. Sometimes you see in regions where you have big soft tissue coverage, that's not really a problem, but in regions, especially towards the ends of your extremities, fingers, metacarpals, wrists, elbows, feet, ankles, every 1/10 of a millimeter plays a vital role if it comes to the to a successful outcome, yes or no. So if you should wonder now why companies come with bulky plates on the market, it simply has to do with the material that those companies are sometimes choosing. So in this case, titanium grade 1, you have to provide a certain width and a certain height to provide enough square millimeters to go over the fracture. And if, like us, if you're in a situation where the titanium grade does not actually play a role for your locking mechanism, and you can use anything that you want to stabilize the fracture, and you can actually use titanium grade 4, for instance, for the plate, or even titanium, aluminum, vanadium, then certainly you can minimize the metal work that you implant into your patient, that you stuff inside. And this then sort of plays a vital role when it comes to suitability of certain implants of certain manufacturers. That's just the way it is, I'm afraid. Okay. Now, the section modulus, this is now a little explanation of what section modulus actually means. It's just a geometrical kind of calculation that you do. So you multiply your width of your product times the height that you square. So you just take the height and just multiply it by height again, and then you divide it by 6. Certain way how to create this kind of formula for you, and I can show you if you want. And now in this little section here, you see is a big difference where your fracture gap is. If you look at this plate here on your left, if your fracture gap is right here where the bar is, there you have a large cross-sectional area of metal, or if your fracture gap actually runs right through the longitudinal slot or through this hole there, because there you only have very little material. So therefore, you have a completely different bending kind of behavior if your fracture gap is where the holes are, or if it's between the holes, also plays a role. And this is just what I wanted to show you there. Now, what the section modulus now means to us, we have to be able actually to calculate sort of the width times the height square. So the important kind of parameter here is what's called the moment of inertia, I. Now, I is there, the height of the product is actually sort of not just squared, it's actually to the power of 3 in this case. And what this shows you is now the difference in behavior if a product is actually implanted flat, or if it can be implanted sort of upright. So when you take a ruler, for instance, and you can do this at home, you know this, right? So a ruler is relatively weak if it comes to bending in the flat plane. Now, if you flip it up 90 degrees and you try to do the same, it's unbelievably sturdy and stable. So therefore, it's not just the cross-section of the product that plays a role, it's actually how the cross-section is actually organized. Is it flat or is it upright? Plays a vital role. You will learn this in a minute. Okay, so those are the kind of things that are important. Those are purely geometrical aspects, or in other words, is also surgical aspect. So where can I actually place my plate? Do I need to place it in a certain position, or can I maybe position it on the side? So where the height or the width of the product actually gives me the stability, and then the thickness of the plate is only a secondary issue, okay? Now, if you take it from there, you will actually see that the orientation of the cross-section now influences the stability of the overall construct. Okay. Now, perfect example for this is Medartis olecranon plating. Now, in the olecranon, we actually use a double plate that we actually apply bilaterally to the region of the olecranon. There's another question there. Are there minimum specifications in Europe? I think this is something that you can answer towards the end, if this is okay, Paulina, if this is all right. Specifications are always the same, by the way. They're all according to ASTM. Question answered. Okay, and yeah, just coming back to this olecranon plating thing. So we thought actually it's way cleverer actually to place a plate bilaterally on an olecranon rather than on the dorsal aspect. Now it appears to be exactly the same thing, so it's a variation in a way, but to be honest with you, it's a huge innovative step. Now, innovation, by the way, actually means when you sort of bring out something that is new, a novelty, basically an innovation. So it's not just enough that it's different, it has to be better to really fulfill what's the true meaning of innovation. Otherwise, it's just a variation of a theme, all right? And then it's pretty boring, okay? Because then you can use the old stuff. An innovative product should always sort of point out certain advantages to you, which means maybe implantation time is shorter, less material that you need to use, easier approach, and all those things make a new product, an innovative product, to an innovative product, and not just to a variation. Now, why is this now so important? Now, if you look at olecranon fracture repair, the classical approach is actually dorsal plating. So you just whack the thing on directly here over the dorsal rim of your olecranon, so right here at the elbow. Right? Now, we all know that this is because you can actually touch this. So if you go into full flexion and you actually knock onto your olecranon, you actually feel the bone pretty much right underneath your skin, plus minus. So therefore, anything that you try to place here is pretty disturbing, especially when you put some weight on. So when you lean actually on your elbow and you have a piece of metal, a big bulky metal inside, this definitely irritates you. There's no doubt about that. I don't think that there's one person on this planet super happy with that approach, okay? So comparing now dorsal plate versus double plate, so basically proving that a double plate is equivalently strong than a dorsal plate is now my little task here, okay? Now, usually, we all know this, whenever we're confronted with something new, we're always a little bit suspicious. Is it really doing the job, or is it, again, just the same thing in a different package, right? We know this happens from time to time. And you buy something that does exactly the same, but just costs more maybe, I don't know. Now, in this case, I would like to point out the advantages of bilateral plate placement. And one for sure, and you can already see this, double plates don't create any kind of material in the region where the bone is most sensitive. So therefore, where the contact region is of your bone to whatever you're actually leaning against. Now, a dorsal plate is always exactly there, right? So this to me is already pretty much of a disadvantage if it comes to dorsal plating. Having said that, it's the most commonly used method. It has been around for God knows how many decades. And the reason for it is relatively simple. So as you can see here, this is a competitor plate that we mounted actually on a plastic bone and from sin bone. And we mounted it actually according to specification. Now we can argue actually about the shape, etc., but don't worry about that. Now, what's more important actually is now to understand the biomechanics of an olecranon or an elbow. So usually you have these comminuted fractures there, so where the olecranon tip sort of completely separates from the rest of the ulna, and sometimes you have an impression zone here, so therefore this gap that's sort of highlighted here in red simply does not exist. So this is all sort of mashed potatoes. So in other words, this olecranon tip has the tendency, mainly sort of driven by the force, the massive force of your triceps tendon that actually sort of attaches right there and is pulling up. So this tip has the tendency to always to rotate towards the shaft, hence, so this gap always wants to close, take it or leave it, or the whole thing wants to dislocate. So this portion wants to be sort of ripped out of its original position. And now the plate, in order to prevent this from happening, this plate has to have a very high stability to do so, because it's actually placed mechanically speaking, in a relatively unfortunate position, to be honest with you. And this means, you see, this is exactly the situation that I've shown you before when we were talking about the sort of the bending resistance aspects, or the moment of inertia. So when you have to place a plate sort of flat on a piece of bone, it's subjected to lots of bending. And if you want to prevent this from bending, you just have to make this relatively thick, right? To stop it actually from bending prematurely. So that's one of the points here. So therefore, your plate has to have a certain minimum height, because titanium or steel only comes in a certain material strength. So you can only kill the forces by actually beefing the material up, make it thick and heavy, okay? And the other thing is obviously what I mentioned before, you have all the contact load actually on your table, wherever you actually get in contact with. So the metal is now always in the way between your table and your bone. So it's very disturbing in that respect. Now, just to quickly show you, this is a little sort of micro animation. So the yellow line that you see there actually shows you the soft tissue and skin before the operation. So here, the soft tissue and skin was pretty much in direct contact with your bone. And after implantation, right, you force basically your skin into a completely new position, and you have to squeeze all the metal work now inside of this relatively tight skin bone construct, where there's no room for that, right? Go into the maximum flexion, and you will see how tight, like tight as a drum, your skin actually becomes. So there's simply no room for a huge, big and bulky implant, okay? Now, if you do the same thing now with a double plate, so you come from both sides and attach it there, obviously you have to release some muscles to make room, right? Because otherwise you cannot just implant the material. And you will now see that even with the plates on, that not the thickness of the plate now is actually the stabilizing factor, but here it's actually the width of the plate, so how broad the plate is, since we actually don't need to place it flat, but we can actually sort of bring it sort of 90 degrees to that. And this means now this plate is so stable because it has a certain height, okay? And so therefore, this is the kind of orientation we wanted to go for, which means we have an extremely high moment of inertia, which therefore means we have an extremely high stabilizing effect. And in terms of skin, this means this is the position of your skin before the operation, and this is the position of your skin after the operation. So metalwork simply is completely out of the way. You can actually touch with your olecranon any kind of table, and you don't actually get any metal between you and your bone, right? That's how it works. So now just a different position, or is less sometimes more. Now usually when you show this for the first time to someone, and everyone obviously who works in this region is used to dorsal plating, so to a plate that is attached from the dorsal side. We'll look actually at one of those plates. So this is one of those plates. There into the camera, so you actually see this. And the first thing that someone is doing, even I do this, right? Give me something to play with, and what I try to do, I try to show you how weak it is, and you find this very easy to bend. Can you see this? It's already bent. Now, is this important? Yes or no? Absolutely unimportant, because this is not how it's actually inserted. It's not actually attached like this. It's actually attached like this, which means we go from a flat orientation to an upright orientation. And if you do a little bit of maths, I will actually show you that there is no difference between this and that. However, the first reaction that you usually get when you show this to someone is always, ah, that's solid, I like that one. I like a dorsal plate because it's nice and strong. I've always used this kind of concept, so that's why I like it. And whatever you show me looks flimsy, and this ain't strong enough to do the job. Okay. Now, why is that? Now, first of all, we trust what we know. So it's a matter of habits, right? If you inserted hundreds and hundreds of dorsal plates it will take you a while to get your head around actually a bilateral approach. So therefore, you might stick still to the dorsal approach because you were happy with it, but at least give it some thought. And we know what we like. Heavy is good, heavy is reliable, and provides strength. That's what we want, okay? Standard thing. Sometimes not really clever. Now, if we compare the cross-sectional area, so if we just look at how much metal sort of cross-section we put over the fracture gap, you will actually find that if you multiply the height times the width of a plate, and in this case, I just measured it and sort of just replace it with just a bar, just for simplification reasons. Height is usually 3 millimeters with the majority of plates that you find out in the market, sometimes a little bit more than that. I don't think that it's less than that. And the width is roughly approximately 15 millimeters. So therefore we have 45 square millimeters to go over or to cover basically our fracture. Now, if we do the same thing now with our sort of smaller plates that are attached from the side, we actually have a material thickness of 1.6 millimeters. So it's a very thin plate, but a plate that has a certain height, and this is in our case 6.5 mil. Now, since we have two plates, obviously we have to add those two together. So it's 6.5 times 1.6 times two plates. This means we have less than half the cross-sectional area for stabilization. And this is usually when you tell this to someone, ooh, they don't trust this. Oh, that's not strong enough. There's too little material there for you. So how can we now prove that our system is still strong enough? Now we have to do a little bit of physics and maths, and we can calculate actually the so-called moment of inertia for the dorsal single and the bilateral double plates. Now we still have the same height and the same width. And if you put now those H and B values here in our little formula, we get an I value of 33 millimeters to the power of 4. Don't worry about the units there. So it's 33. Now, if we do the same thing now on those upright plates, because they're upright, now it's the heights, so the 6.5 that are actually taken to the power of 3, and the width or the thickness with 1.6 millimeter, you have a much, much higher moment of inertia, okay? So maybe you haven't expected that, but this is usually what you feel when you go from there to there. This is exactly what you feel, moment of inertia, okay? Now, if you take this then a step further and we calculate now the so-called bending resistance, W section modulus. So here we take again our I, our moment of inertia. But here now it's important to us to know exactly where's the neutral line of the metal. Now here in the flat orientation, since this is 3 millimeters in height, this neutral line has a position of 1.5 millimeters away from the contact zone. In the upright, though, this is 6.5. This has a distance from 3.25 from there all the way to there. Now, if we put this now into our formula, and now comes the fun part really, you will actually find that the bending resistance W 22.5 is perfectly identical to those two plates, although we only provide less than half the cross-sectional area. So bending wise, we're doing exactly the same thing, no difference, but we're not disturbing any soft tissue and we implant less material. And that's now the beauty, obviously, of these new concepts. So if you do now the volume and mass calculation, so how much titanium we actually stuff inside of a patient, you will actually find that in this concept, we only need about in this concept, we need 3,600 cubic millimeters if this would be 80 millimeters long, whereas with our construct, it's only 1,664, or calculated now in weight, right, in titanium weight. This implant weighs about 16 grams, whereas those two plates together, so both plates together, only weigh 7.5 grams. So it's less than half, but the stability is exactly the same thing. And to me, this is a huge step in the right direction, because again, we're not designed to hold any foreign material in us. We're optimized in terms of how much foreign material we can actually accept. And to me, this is where it needs to go. Okay, next point, stiffness. Now, stiffness is an important parameter when it comes to materials and structures. Stiffness is usually sort of a material value for a piece of material, whatever material this is, but it also describes a structural stiffness. So when you screw a plate onto a piece of bone, then you have a stiffness of the overall construct. So plate together with bone. All right. Now, how much the object actually deforms under load is an important aspect for us. So is it actually deforming at all? So do we have flexible deformation? Do we have a plastic deformation? And how does the object actually share or transfers loads now to other materials? So how is the load transferred from bone to metal and from metal back to bone? What's happening now in those interfaces? Those are the important points. So the relevance of stiffness of an internal fixation depends therefore whether we will experience a significant mechanical load, tension, compression, or torsion, whether the performance is affected by the amount of deformation. So therefore, is the force actually sort of changing anything on the material, and how does the implant actually share the load to the bone? So these are the things we need to look at. Now, very often you see when tests are actually performed, we have sort of static tests where you just put load on a piece of metal, right? You have a plate, and you put the plate into a testing machine, and then you load the plate or the plate and screw construct until it eventually fails. This is the typical sort of load to failure test as we see, or on this camel that you see here on the left-hand side, is how many straws can you actually put on the back before it completely collapses. Okay, now does this tell us anything about the behavior inside of a patient? Most possibly not. It will just tell us how strong the plate is. Is this important? To be honest with you, not really. Okay, that's why to me comparative tests where you compare competitor A, B, C, and D, and if it comes purely to strength of the metalwork, does not tell me anything about its clinical behavior. So that's irrelevant if you ask me. More importantly though, is what happens if you have a dynamic stability test. So therefore, when you cyclically load an implant, so you load it, you unload it, you load it, you unload it, ever and ever so often, and at least it gives you a different aspect of how flexible the implant is, for instance. So therefore, static stability may be important, maybe not, but dynamic stability, different thing, because now we can actually judge the lifetime of a product. Is it already failing after 10 load cycles? Not a good thing, even if it's super strong, not what we want. Or is it actually surviving a relatively long number of load cycles that you apply? So those things are, I think, way more important if it comes to that. Good. Now, practical example number 2, proximal humerus. Proximal humerus, as you know, is a critical joint, okay? Especially a typical fracture of elderly females. So therefore, you have a very osteoporotic situation in the humeral head. And since your implant also here has to take bending, shear, compression, tension, and torsion, and upon the application of bending moments, maybe not that much of axial loads, but mainly bending moments due to the rotator cuff muscles, etc., we have a certain action, right? So the action forces that are applied by your muscles actually pulling on the head, and you have a reaction now inside of your bone. So basically what's actually connecting the head now to the metalwork are those screws. So therefore, when you start now pulling and twisting and turning, you have a certain reaction. So you have a certain pull out component, and you also have a certain shear component. So your screw sits there and the force is actually applied, which can actually lead now to a sintering effect, so that the bone is slowly but surely running through your screw if the patient is very osteoporotic. So those kind of things need to be investigated. So just talking about the stability of the actual implant as such, unnecessary knowledge, okay? What we need to know is what's happening now in the interface. What's the reaction now inside of the bone? Because at the end of the day, we want to treat patients, right? We are not here to sort of check out the performance of metalwork. If this would be the case, I would build implant plates that are 20 millimeters in thickness, but that's nonsense, doesn't mean anything, okay? Right, next. Now, since we know that in the proximal humerus, obviously, the bone is very brittle and not very stable, you have to provide lots and lots of contact points. So the more the merrier in that respect. So the more you actually can shoot your implants, screws, into regions where you get a little bit of purchase, this is where you want to go. Now, there are systems actually out in the market that come with so-called calcar screws. So here's the calcar region. So for stabilization, this is where you would like to seat your screws. Now, we have for very critical patients, so where there's the very high risk that the head of the humerus actually sort of tilts in varus, so basically tilts towards medial. There we can actually sort of place what we call a spiral blade inside. So it's basically, it starts upright and then spirals up towards the calcar region to provide a large contact surface for the very soft bone rather than just two screws that only provide a relatively small surface. So we have some kind of pedal inside, whereas our competitors, they tend to have sort of just screws inside, like a broomstick compared to a pedal when you go actually on a boat, okay? Now, we can certainly use our implant without spiral blade. That works perfectly well, but for the critical kind of situations, we can potentially also use the spiral blade. But since every time you go into sort of designing something, you need to know about the post-operative challenges that usually a patient has to go through, or a surgeon at the end of the day, right? And those typical things that you can find in literature when it comes to proximal humerus head repairs, lots of reduction, varus of the humeral head tends to turn inward. Avascular necrosis is one of the problems. Secondary screw perforation in the joint, those typical cutout things, so that the screws actually end up in the joint eventually. You have pseudarthrosis, for instance, when the implant is way too stiff, so the bone simply does not want to heal. Screw loosening inside of the bone, so these typical sort of cut through problems, or teeth wiring problems. You can also have cutouts. Then plate breakages. If you have a prolonged healing period, a plate can also break, right, after so and so many load cycles. Subacromial adhesions, capsule shrinkages, so all those kind of things you can actually find in literature. Now, the red paragraphs that I've pointed out, those are purely implant parameters. And implant parameters means we can actually play with them. So we can do something about that. I cannot do anything about the avascular necrosis. Maybe not drill as many holes, maybe this helps, but usually there's not really much that you can do in subacromial adhesions. What can you do? Just happens. Now, implant parameters, this is where we are at home, okay. Now, what we've done, we did a little comparison here, and we used one of our plates with a spiral blade. We used one of our plates without the spiral blade, and we used a famous competitor in comparison. We put in 6 implant screws in this setup, and in this setup. So we had exactly the same number of screws inside. The only difference was here with the spiral blade, we had an additional blade inside. That's why it's not fair to properly compare, but the effect that this has is quite interesting to see. Now, so here we were not interested in the behavior of the metal, completely unnecessary information. What we want to learn is what kind of effect there has now flexibility and elasticity, which our plates seem to have, compared to a rigid product, which our competitors tend to provide. So therefore, we had to use an extremely soft material to mimic the bone, if you like. That's a polyurethane with an extremely low density. so to mimic basically an osteoporotic patient. So it's so-called PCF5. So it's like a sponge. So you can even with your finger, you can just poke a hole inside if you want, so soft it is. We applied an axial load of 275 newtons, so 27 kilograms roughly. We had certain parameters. So we said after 160,000 load cycles, we stop the test, or as soon as we have a displacement. So as soon as we have longitudinal slots inside of the bone that are greater than 6 millimeters. This is also when we would have stopped the test. We had a two-part fracture. Force was purely axial, so the simplest kind of setup without any torsion and moments, etc. Just pulsing, simple. Okay, don't want to overcomplicate things. Now, what happened? Now, this is now a super interesting graph here. So those are the basically the materials after the test. So we always had a little bit of cut-throughs, so cheese wiring effects, but to us it's now important, when did these things happen? Now in a rigid plate, and the competitor plate was very rigid, you could already see that after the first few thousand cycles, with every extra cycle, those longitudinal slots very quickly sort of increased in length. So after 30,000 cycles with our competitor plate, we nearly reached the end of the test with 6 millimeters, okay? So we had this very quick failure in soft bone, whereas with our plate, so, and this is now the plate without spiral blade, so 6 screws inside, 6 screws inside, so we had exactly the same setup. But since the implant was more flexible, right, those forces had not been compensated by the plastic itself, but a certain energy was actually stored in deforming energy of the implant, but elastic or flexible deformation. And when you took the load off, this deformation was actually sort of fed back to the system, which means it acted more like a spring, right? Like in a car, a suspension, right? Rather than something like a bicycle that where every bump that you get from underneath is directly converted, bang, to your saddle. So you get it directly into your spine. You can actually feel this. Though if you have a suspension, then certainly you have lots of deformation there. And this is now, that's something that you can actually see. So even after 150,000 cycles with this system, we just about reached 5 millimeters. And with a spiral blade, because obviously we had a much larger area now to sort of compensate now the cut through problem. So with a spiral blade, we ended up obviously with a much longer lifespan. So even after our 150,000 cycles, we just had longitudinal slots with a length of maybe 2 to 3 millimeters at the most. And this to me just demonstrates how big the difference can be between something that is rigid. So therefore, maybe in terms of static loading, the competitor plate and our plate would have behaved perfectly the same, potentially, I would think, but under dynamic load, very different. Those are the things that I find worthwhile to highlight. Okay. Now, next conclusion. Static stability, therefore, does not tell us much about the suitability of a stabilizing item at all. Dynamic load, though, shows the weakest link of the overall construct stability, and therefore gives you a much clearer statement towards the interface metal to bone. And this is what we always should actually bear in mind. We're actually putting a dead piece of metal into living tissue. So at least we should have some kind of interaction between the bone cells and the metal work. Okay, and I think that's perfectly clear. So therefore, when evaluating behavior inside of bone, the substrate also has to reflect the stability or density of the bone. So it's no good if you just screw this on a piece of wood, because a piece of wood is a piece of wood, it's not a bone. And so therefore, if you want to properly test this, you always have to calculate basically worst case. So use something that is soft. Now, the better the load can be distributed over a large contact area, obviously the less likely a cut through is to be expected, and therefore high rigidity leads to a premature failure, especially when you have very osteoporotic patient collective in front of you. Good, just to continue, so I don't want to use up too much of your time, obviously. A little excursion towards what means now orientation of a plate, so flat side and upright side. So in a mandible, maybe some of you are max surgeons, I don't know. But just in a mandible, you have once in a while the situation that you have a patient with a mandible that is too short, you have a retrognathia of the mandible, so therefore you have to transport the mandible forward in order to get a proper occlusion of the maxilla and the mandible. So therefore you have to somehow sort of separate the body of your mandible from the what's called the ascending branches and to mobilize then therefore the body. Okay, so this is demonstrated here in a little animation. So I do this Z kind of oblique dalpon osteotomy. And when you transport now the body forward, you will now find that there is a certain effect. So there's a certain translation. So the further the jaw or the chin region is actually sort of transported forward, the more those condyles are actually forced in a new position. Can you see this? Okay. Now this new position would actually mean that your condylar heads are actually sort of pushed outward in the joint capsule of your fossa. That's very painful for the patient, and this is obviously not what we want to do, but what we want to seat those condyles back into their original position. So therefore you have to somehow angle now those joint bearing parts. Now there are the classical methods with those screws. This is a very rigid kind of system. So therefore you have to be very careful before you insert those screws. So in order to recreate the position of your two condyles relative to one another, if they're slightly off, then your patient sort of experiences some kind of subluxation. They're very painful and so forth. And that's not what we want. Or rather than having obviously something that is super stiff, you could potentially go for a plate that you screw on from the lateral aspects, and you insert screws at the body part as well as in the ascending branch here. And this plate, if you choose it thin enough, allows now for certain motion. So you allow basically your condylar heads to seat themselves in a more or less anatomical position without actually forcing them into an unwanted position. This is a good thing to have. Now, the main stress of mode in a mandible is obviously bending, right? So when you start chewing, then, and your masseter pulls up, then your whole mandible is obviously subjected to a bending load. So when you try to stabilize now the body to the ascending branch, then obviously, and you use a plate and you start chewing happily along, then this plate would just bend like a banana. So very similar actually to a weightlifter, right? When you watch a weightlifter and they have a bar in the hand, you can actually see how the whole thing completely deforms. That's not what we want. So a plate that looks like this, for instance, so if you want to stabilize now the tooth bearing part to the joint bearing part, and you have a plate that looks like this, then it's very easy to bend, because here you just have a very small cross section to take now the bending load. So not a clever design. The same thing, obviously, so this is the weak spot here, which has to do again with the moment of inertia. The same thing goes with this kind of plate. Looks squiggly and more stable, but at the end of the day, the cross-sectional area is exactly the same. So therefore, you have the same problem. So therefore, this is again your weak spot, right here in the middle, not what you want. What you want, though, is obviously something where you sort of can transfer the bending into a tensile load and in a compressional load. Now to look at this double plating construct. So when you apply now a bending here, then the upper plate will actually take the tensile load, whereas the lower plate is more subjected to compression, all right? This comes typically from I-beam. So when you're in architecture and you look at an I-beam, how an I-beam works. So when you put load on an I-beam, you have a compression side and you have a tension side, or on this structure that you see there. Right, and this is exactly what we tried to mimic here. So we had this double or this open plate construct. So therefore, rather than having just a single bar crossing, we have now two bars. So when you apply now a bending load here, then you have basically a tensile load in the upper bar and a compressional load in the lower bar. But since it's only 0.7 millimeters in thickness, we still allow those condyles to seat themselves. So we have a high stability in the chewing plane, but very little stability in the seating plane of your condyles. So therefore, we made the most out of that. Okay. And the same obviously also goes for those grid constructs or grid concepts. So when you compare a standard old Reco construct for sort of bridging a large defect, and we used to do this with a titanium grade 4 plate that was with a very high thickness, so very difficult to bend, unbelievably stable. And we tried to replace this with a very soft plate that is very thin, but had a grid structure, so therefore had a tensile side and a compressional side. And believe it or not, when we tested the whole thing and we compared this to that, you see, with the super strong product, we could only perform 130,000 cycles at a maximum load of 323 newtons. And we tried also to kill this plate here, but we figured out, first of all, we could do way more cycles and we could even double the load. Although the material is much softer, therefore much easier to contour around the mandible. So therefore, geometry in this case means everything for us, and obviously what kind of metal we can actually choose. And last but not least, calcaneus plate. Again, we compared our calcaneus plate that sort of has a grid structure or a frame structure that sort of holds all the forces in a framework, rather than having a typical bar construct that you find here in the Sanders plate construct here, right? So we had a multi-fragmented fracture. This was the same here as well as here. And when we loaded then the whole thing, more or less anatomically, so we had the pressure point here at the tip of our calcaneus, and then we applied here in the subtalar joint. We applied then obviously a pulsing load, and we had the effect that the Sanders construct, that was a standard thing, died relatively early. So after 50,000 cycles at just 100 Newton, I would say 100 Newton is 10 kilograms, okay? Don't forget, 10 kilograms is nothing, okay? And after 50,000 cycles, the Sanders construct already died and displaced 3.5 to 4 millimeters. So the whole thing just twisted and turned, right? So therefore, the likelihood of having a good healing is most possibly not what we want to see. Whereas with our plate, we could ramp the whole thing up. So we could go 150, 200, 250, 300 newtons, nearly 400 newtons before our system, so nearly 40 kilograms, and 90,000 cycles or 100,000 cycles before ours actually sort of lost it. So to me, this is a clear sign. If you have a good design, if you have a clever orientation and geometry of your construct, you can always outperform the stuff that's already out there, but you have to understand how the construct actually works. Now, having said that, as a conclusion, there are implant systems or sometimes individual plates that are more suitable than others. This is something that can be stated, but still, I believe very much that completeness of a system, because buying a system means you want to treat pretty much everything that you can find, that you see during your daily routine in a hospital, and suitable plate design seems to be really the key to a good product. But having said that, obviously, you see, I don't want to be in a position to tell you that we are doing it right and everyone else around us is doing it wrong. At the end of the day, I think every company is trying to do a more or less good job, okay? It has to do with the standard, obviously, etc., and how far you want to go, how much money you want to invest in research, etc. You want to be fast on the market and be a Me Too guy. It's a decision. Or do you want to do it perfectly right, close to 100%? Then obviously you need longer time, you need more money. You cannot sell your product for very little money, obviously, because somehow you have to sort of have a certain return of investment. But there's always one saying, I say, There is no guru, no teacher, no method. At the end of the day, a surgeon has to find the ideal method that works for him. Everyone has a certain qualitative understanding how well something has to be sort of recreated anatomically. And if you have to do with something who is a perfectionist, they're never happy with anything. And if you're the one who just want to have it done with, then obviously then maybe a cheaper product is also doing the job for you. And with this, ladies and gentlemen, this was my last slide. Thank you very much for your attention. I hope you enjoyed this. I did. I always do, as you can tell. I never stick to my time. Sorry. But I enjoy talking about these things, and I would love to have a Biomechanics 3 session, because I've still got so many things in my head, so many rabbits that I can pull out that I would like to share with you guys. So once again, thanks very much. I think a few questions that I maybe would like to concentrate on that came in during the session. Actually, one came from Paulina. Are there minimum specification requirements in Europe for titanium grade for medical implants? And a standard or norm? Yes, there are. Obviously, the ones that I've shown to you, this ASTM F67 for commercially pure titanium, ASTM F136 for titanium, aluminum, vanadium, for instance, those are American standards. So this gives you the chemical composition in terms of how much foreign material, how much iron, how much aluminium, how much vanadium, how much oxygen is actually allowed to be part of the metal structure, and this is clearly stated there. So we certainly can only work with material that is produced according to ASTM F67, F136, and we need to have a certificate for this. Otherwise, it's just a piece of metal for us. We can't use it for anything. So we need to have fully certified material, and only then we can actually sort of obviously make our implants from that. And there was another question from Robert. Question is, how come that with proximal humerus plate, the competition is weaker than ours in terms of flexibility and material? I'm not quite sure what product you're referring to. What I know, the plate that we have been testing is as strong as ours, but in terms of flexibility, it's just way too rigid. It's not flexing under load, it's just sitting there rock solid. So when you load now the bone, rather than the whole construct obviously pulsing under weight or under load, this construct is just sitting there. So, and your bone, bang, 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 has to compensate now. And slowly but surely, just sort of running through like a butter through a knife, okay? And this is what too much rigidity can actually do for you. So a good balanced system always takes the stability, obviously, of bone into consideration. Otherwise, you see, it's not, I would say, not really a design that is calculated that well. Okay, I hope this is doing the job for you. If there are no further questions, thank you very much for all your attention. Please stay safe and healthy. Wear your safety things, right? And I hope to see you soon again. You see, obviously doing this in virtual space is fun, but it's not replacing, to be honest with you, it's not replacing the kind of atmosphere that we have if we are sitting together and we can actually discuss things. This is not a replacement for it, but it's definitely better than nothing. All right. So with this, thanks very much for your attention. Enjoy the evening or the rest of the day, whatever time zone you come from. I have now 6:15. So I hope you enjoyed this. I did very much. Have a nice day and hope to see and hear you soon. Take care. Bye-bye.